this lesson, we are going to talk about rates of change and behavior of graphs. The rate of change describes how an output quantity changes in the relation to what we input into our function. We always write our rate of change as the outputs per the number of inputs that are written. Sometimes our rate of change will fluctuate based on the type of function or graphs or information that we are given. So depending upon the inputs that I choose, the average rate of change might fluctuate from piece to piece, so be careful. We say that the average rate of change can be written on a specific interval, AB, given the change in Y, or the change in our outputs, divided by the change in our inputs, or our X value. Typically, you will see this particular formula, the change in Y over the change in X, as slope, and we'll talk more about that in our lesson 1.4. However, in this lesson, if we are given a specific interval, another way in which we can write slope of those two intervals is by evaluating each piece of the interval and dividing it by the difference between the particular interval. So looking at our graph below, the function C of t gives the average cost in dollars of a gallon of gasoline t years after 2000. So if I'm looking at t, my row t, 2 years after 2000 would be 2002, 2003, 2004, etc. What is the average rate of change from 2002 to 2009? So I'm looking from 2002 to 2009. As I'm looking at my graph, I notice that I'm increasing, but I'm not increasing by the same amount each year. And then notice here, I'm decreasing. So for the first years, I'm increasing and then I'm decreasing. So I'm looking for the average over all of these years. What was the average rate that we changed? We're not looking at a particular constant rate, but an average rate I'm looking for. Thus, I can say that C of 9, because it's 9 years after 2000, minus C of 2, 2 years after 2000, over 9 minus 2, because my interval that I'm specifically looking at is 2 to 9. And of course, we have our given values. I've got $2.14 minus $1.47 divided by the 7 years in between these two. So approximately 0.0967. What does this mean? This means that on average, the price of gas increased about almost 10 cents, but 0.0967 cents per year, because we divided it by 7 years, so it's per year. Similarly, what is the average rate of change from 2007 to 2009? So now I'm going from 2007 to 2009. So from here to here, what was my average rate of change over these two particular years? So C of 9 minus C of 7, and then 9 minus 7. So I've got 2014 minus, $2.14 minus $2.64 divided by those 2 years. In this instance, we actually lost 25 cents, because notice I went from 264 to 301, and then we dropped. So over, what is the average over these two particular years? So we would say that on average, the price of gas decreased 25 cents per year. And you could even say between 2007 and 2009. So you could be specific about what specific time frame we're talking about. What about if we're given a particular graph itself? So given the function g of t shown here, find the average rate of change on the interval between 0 and 3. So 0 is our a value and b is our 3 value. So I have g of t, I need g of 0. So when we're at 0, we are at 1 for our output. And then g of 3, at 3, we're at 4 for the output. So now we have everything that we need to write our function or our average rate of change. So f of b minus f of a over b minus a. Thus, we will have 4 minus 1 over 3 minus 0, 3/3 or 1. So the average rate of change between 0 and 3 is an increase of 1 unit. On a road trip, after picking up your friend who lives 10 miles away, you decide to record your distance from home over time. Find your average speed over the first 6 hours. So we want to go from starting at 0 to 6 hours here. And we're looking for what is the average speed. So we're going to have miles over hours. Thus, I'll have d of 6 minus d of 0 over the number of hours, 6 minus 0 hours. 292 miles that are associated with 6 minus 10 over 6 gives me 282 divided by 6, so approximately 47 miles per hour over the first 6 hours. Now, if I did the same thing over the full 7 hours, over the first 2 hours, the middle 2 hours, this change might be different. Your average speed might change, right? You think about driving to a location. If I drove from Valley City to Fargo, there are certain times that I'm going faster than others. There are currently two pieces of construction going on where I have to slow down to 40 miles per hour. So my speed slows down. So I could think about what is the average rate of time it took me in order to get from Valley City to Fargo. Who cares about the slower speeds in between? I can determine what was my average speed throughout my entire trip. But knowing that independently within that trip, there were pieces of my trip that were going slower or faster than another. Compute the average rate of change of the function x squared minus 1 over x on the interval of 2 to 4. So this is my a value and my b value. I first need to identify what is f of a. And in this case, f of 2. So 2 squared minus 1/2 is 4 minus half, or 3.5. And then f of b is f of 4, which is 4 squared minus 1/4, or 16, minus 1/4, which I know is 5 3/4. So if you wanted to turn this in, so 3.5, and then 15 75/100. Now we have all the pieces that we need. I can say f of 4 minus f of 2 over 4 minus 2. Thus, 15.75 minus 3.5 divided by 2 gives me 6.125 units. Doing the same idea except putting it into context, the magnetic force, F, is measured in newtons between two magnets, is related to the distance between those two magnets in centimeters. Using the formula, F of D is 2 over D squared. Find the average rate of change of the force, the distance between 2 centimeters and 6 centimeters. So I'm looking for 2 to 6. So I'll first start off by finding F of 2, which is 2 over 2 squared, or 2/4, which is 1/2. And then I'll also find F of 6, which is 2 over 6 squared, or 2 over 36, which reduces to 1/18. Now we have all the pieces, so F of 6 minus F of 2 over 6 minus 2, thus 1/18 minus 1/2 over 4. This is the same as 1/18 minus 9/18 over 4, which is negative 8/18 times the reciprocal of 1/4, or negative 1/9. So I can say that the average rate of change of the force, I should say of force, is negative 1/9 newtons. I could say decreases by 1/9 newtons per centimeter. And if I use the word decreases by, I would want to get rid of this negative, because that would, if I say decreased by a negative, that would negate itself and turn into a positive. So decreases by 1/9 of a newton per centimeter. Find the average rate of change. We've got ourselves a quadratic here on the interval between 0 and A. Oh, this is interesting. Our solution will involve A. It no longer do we have a number. So let's think about what this might look like if I evaluate my function and say g of 0 will give me 0 squared plus 3 times 0 plus 1. Which is just 1. And then g of A is a squared plus 3a plus 1, which there's nothing else I can do. So what does this look like? I'll have g of A minus g of 0 all over A minus 0. Well, g of A is a squared plus 3a plus 1 minus g of 0, which is just 1, over a minus 0 is just a, because I'm subtracting nothing from it. I also have plus 1 and minus 1. I also see that I can factor. I have a greatest common factor of a, leaving me with a plus 3 over a, which now allows me, since I have a common factor in my numerator and denominator, to eliminate these a's, leaving me with a plus 3. Your answer will be an expression involving a, was our hint that we do just have a plus 3 left. Marginal cost is typically defined as the change in total cost if the quantity of items produced is increased by 1. Likewise, marginal revenue and marginal profit are the change in revenue and profit if the quantity of items is increased by 1. So we're increasing by 1, and we're finding that the change that's happening. So a company has determined the total cost of producing Q items is equivalent to 2,000 plus 50 times the square root of Q. Find the marginal cost when production is currently at 5,000, but we want to increase it by 1. So I want to find what is the average rate of change if I go from 5,000 items to one additional item, 5,001. So we're going to change our quantity from 5,000 and get a value and see what happens. Times the square root of 5,000 gives me approximately, and I'll let you check that with your calculator. And now we need to do it also with one additional item. We just get a few pennies more here. Thus I can take and use my average rate of change over, and all we did was increase 1, so 5,001 minus 5,000 gives me divided by 1, of course. It gives me that the marginal cost is 36 cents. So what does this mean? So we can think of this as a secondary option. So after producing $5,000 items, this tells us that the additional cost of producing one more item, or the 5,001st item, is 36 cents. Switching gears a little bit, it's important to discuss where our graphs are increasing and decreasing, which will help us identify some pieces coming up in subsequent sections. So a function is increasing if the inputs are increasing, as the inputs are increasing, the y outputs are also increasing. So notice as I'm going along on my graph here, my y values are also increasing, so my graph is increasing in this portion. However, my graph is decreasing as my x values are increasing, my y values are decreasing. So here is an example of decreasing as well as here. So as my x values are increasing here, my y values are decreasing as we go left to right. So given the function graphed, on what intervals does the function appear to be increasing? And we're going to do both increasing and decreasing here. So as I look at my graph, as I'm coming from the y, from negative infinity here, I see that my graph is decreasing all the way until I hit 1. Then I switch gears and I'm increasing for a little bit until I hit 3, which now I'm slightly decreasing until I hit 4. And then I'm going to be increasing forever and ever as I continue on to positive infinity. So where are the pieces in which my arrows are going up? My arrows are going up from 1 to 3. And notice I'm using parentheses. When we're talking about increasing and decreasing, we only want to utilize parentheses. Then I skip over some because then we were decreasing, and then I'm increasing again, starting at 4 all the way until positive infinity. So these two locations here and then here, which would go that direction. And I'm using my x-axis to represent my values. Where am I decreasing then? Well, we started decreasing. I'm coming from negative infinity on my x-axis, and I am decreasing all the way until I hit 1. Then we were increasing, and I began decreasing again in this little area from 3 to 4. And then I no longer was decreasing. If I had another section, I'd put a union and continue on forever. Notice that within each increasing and decreasing, and I'll get rid of all of my mess here, that when I switched from increasing to decreasing, there were what we would call local maximums and minimums. So at each increase and decrease section, there was a minimum and a maximum within the graph. So anytime you're switching from increasing to decreasing or decreasing to increasing, there will be a minimum or a maximum. So a point where the function changes from increasing to decreasing is called a maximum. When we go from decreasing to increasing, we call it a minimum. And when we combine them all together, we call them our local extrema. So in the picture on the right, we are changing from decreasing to increasing. So we have a minimum. We also are going from decreasing to increasing, another minimum. And then we go from increasing to decreasing, we have a maximum. And then increasing to decreasing, we have a maximum. Let's see what that looks like when we put it with some graphs and some other tables. The function below gives the same cost in dollars of a gallon of gasoline in 2 years after 2000. Find the interval in which the function appears to be decreasing. For the sake of the problem, we're also going to talk about increasing, just so that we can get in a practice doing both, and then estimate any local extrema using the tables. So notice that we're increasing, getting larger. Our y values are getting larger as our x values are getting larger. Uh-oh, now we are decreasing as our x values get larger. So we are increasing from 2 to 8, and then we switched to decreasing from 8 to 9. We don't know what happened after that, so we can't make assumptions. Thus, because we switched from increasing to decreasing, we have a maximum when t is equal to 8. We could also say that the maximum is at $3.01 as well, depending upon how they want it written. Use graphing technology to estimate the local extrema of the function. So again, the local extremas, the minimums and the maximums. And then determine the intervals on which the function is increasing and decreasing. What's really great about Desmos is that I just plunked in 2 over x plus x over 3, and it gave me some gray points on Desmos where I was able to tap those points and find their locations, which gives me their maximum and minimum. So notice I am increasing here, and then I immediately go to decreasing. So because I'm switching from increasing to decreasing, I have a maximum at negative 2.449, 1.633. Here I am decreasing. I hit that point and then I go back to increasing. So decreasing to increasing, I have a minimum. at 2.449, 1.633. Oop, and this one was negative, excuse me. Now it's asking us to determine where we're increasing and decreasing. So I have two places where I'm increasing on the left here. So as I'm coming from negative infinity all the way until I hit this maximum. So I'm increasing from negative infinity all the way until I hit that maximum. I'm going to say union. I'm going to hop over, and now I have to start at this minimum, and then I'm increasing again from that x value all the way to positive infinity. So 2.449 to positive infinity. Where am I decreasing? I am decreasing starting at this maximum. And notice I'm getting very close to 0, but I'm never going to touch 0 on my x-axis, so it's an asymptote. And then I'm also decreasing from 0 because I'm hopping over 0. I'm hopping over like this whole area here. So I'm getting close, but I'm never going to touch all the way until I reach 2.449 on my graph itself. And let's use graphing technology one more time to estimate the local extrema of the function and then determine the intervals on which the function is increasing and decreasing. This one's a little nicer, as nice whole numbers instead of decimals like the last example. But I am increasing, I'm hitting this maximum because I'm switching then to decreasing. I'm now going to hit a minimum because I am switching to increasing. So as I think about my movements along the x-axis, when I'm increasing, I'm coming from negative infinity all the way until I reach -1. I'm hopping over a bunch, and then I started increasing again, starting at my x value of 5 until I reach positive infinity, because I'm never going to stop, right? I'm going to continue. My x values are going to continue increasing as my y values are also increasing. But I have a small place where I am decreasing. I am decreasing in between -1 and it looks like 5 here. So as my x values are increasing, my y values are decreasing in between -1 and 5.